The skies over England trembled with the roar of engines as wave after wave of German bombers crossed the Channel in the summer of 1940. The RAF fighters rose to meet them, but their pilots faced a grim reality. The Luftwaffe aircraft could climb higher, fly faster, and maneuver with deadly efficiency. British fighters struggled to keep pace, their engines sputtering and knocking as pilots pushed them to their limits. The battle for Britain's survival was being fought not just in the air, but in the invisible realm of molecular chemistry, deep within the fuel tanks of every aircraft that took to the skies. What few realized at the time was that this technological gap would be bridged not by a new aircraft design, not by a secret weapon, but by something far more humble and yet revolutionary. A liquid that most would have considered waste, transformed by the minds of a handful of chemists into what would become one of the most crucial factors in Allied victory. This is the story of how aviation fuel changed the course of the Second World War, and how one man's work with what others called impure sludge gave Allied bombers the range to strike deep into the heart of enemy territory. Before we can understand the revolution, we must first understand the problem. In the late 1930s, aviation fuel was a relatively simple product. It was refined through basic distillation from crude oil, a process that had changed little since the earliest days of petroleum. The resulting gasoline had what was called an octane rating, a number that measured its resistance to a phenomenon that pilots and engineers dreaded more than almost anything else. Knock, engine knock, or detonation was the sound of an engine destroying itself. When fuel ignites too early in the combustion chamber before the piston reaches the optimal position, it creates a shock wave that hammers against the cylinder walls. The sound is distinctive, a metallic rattling that every pilot learned to fear, because once that sound began, it meant metal was grinding against metal, pistons were being damaged, cylinder heads were cracking, and engine failure was imminent. At altitude over enemy territory, engine knock didn't just mean a forced landing. It meant capture or worse. The octane rating system had been developed in the 1920s by an American chemist named Graham Edgar. He created a scale where pure normal heptane, which knocked terribly, was rated 0, and pure isooctane, which resisted knock beautifully, was rated 100. Any fuel could be tested and compared to mixtures of these two reference fuels to determine its octane rating. By the mid-1930s, automobile gasoline typically rated around 40 octane. Aviation gasoline was much better, but still only rated between 70 and 87 octane. In 1939, as war clouds gathered over Europe, the Royal Air Force was using 87 octane fuel in its fighter aircraft. The German Luftwaffe, however, had access to slightly better fuel between 91 and 100 octane. This difference, seemingly small on paper, translated into a significant advantage in the air. German fighters could generate more horsepower without their engines knocking. They could climb faster, fly higher, and outrun British aircraft in many situations. The Messerschmitt 109 could reach speeds the Spitfire and Hurricane simply couldn't match when both used their respective standard fuels. But something remarkable was happening across the Atlantic Ocean, in the industrial heartland of America. A series of breakthroughs in fuel chemistry were about to change everything. And at the center of this revolution was a French immigrant who saw potential where others saw only waste. Eugene Houdry had been born into a wealthy steel manufacturing family in France in 1892. He studied mechanical engineering and became fascinated by the problem of converting crude oil into usable products. The traditional method of distillation had severe limitations. It could only extract the lighter fractions that naturally existed in crude oil. The heavier components, the thick sludgy residue left behind after distillation, were considered worthless. Refineries burned it as fuel or simply disposed of it. But Houdry believed this waste could be transformed. He experimented with catalysts, substances that could speed up chemical reactions and break down those heavy molecules into lighter, more valuable ones. After years of work, he developed a process called catalytic cracking. By heating heavy petroleum fractions in the presence of special clay catalysts, he could break down their large, complex molecules into the smaller molecules that made up high-quality gasoline. And not just any gasoline. The fuel produced by catalytic cracking had remarkably high octane ratings. In 1930, Houdry moved to the United States and partnered with Vacuum Oil Company, later part of Saucony Mobile. He continued refining his process, and by the mid-1930s, the first commercial catalytic cracking units were being built. The process was expensive and complex, but it could do something no other method could. It could turn nearly worthless crude oil residue into premium aviation fuel with octane ratings approaching 100. At the same time, another American was becoming obsessed with high-octane fuel. James Harold Doolittle, known to everyone as Jimmy, was a legend in aviation circles. He had earned the first doctorate in aeronautical engineering ever awarded by MIT. He had won the Distinguished Flying Cross for record-breaking flights. He was a champion air racer who pushed aircraft to their absolute limits, and in that racing, he had learned firsthand the difference that high-octane fuel could make. In 1930, Doolittle left active military service and joined Shell Oil Company as manager of their aviation department. He immediately began pushing Shell's executives to invest in high-octane fuel production. Most thought he was crazy. High-octane fuel cost as much as $30 per gallon to produce in small research quantities. Motor gasoline sold for less than 20 cents per gallon. Who would pay such outrageous prices? But Doolittle persisted. He used his fame and connections to lobby military leaders and government officials. He demonstrated the benefits in dramatic fashion by setting aviation speed records and winning air races using 100-octane fuel. Slowly, he convinced Shell to scale up production. By 1934, the price had dropped to around $2 per gallon, still expensive, but no longer impossibly so, and the U.S. Army Air Corps was paying attention. Meanwhile, in the oil fields of Texas, another piece of the puzzle was falling into place. Sun Oil Company operated a refinery in the southeastern part of the state, near Beaumont. There, a chemist named Tim Palooka was working on his own approach to producing high-octane fuel. He adapted Houdry's catalytic cracking concept and developed what became known as the cracking tower, a vertical column where heavy petroleum could be broken down continuously rather than in batches. Palooka's innovation made production more efficient and economical. Sun Oil began producing 100-octane aviation gasoline in significant quantities. They called it Sunoco Blue, and it represented a breakthrough in making high-performance fuel available on a commercial scale. The technology was spreading, and American refineries were investing heavily in the infrastructure needed to produce these advanced fuels. But perhaps the most crucial contribution came from a team of chemists working at Standard Oil Company of New Jersey, which would later become Exxon. Led by Dr. William J. Sweeney, this team was tasked with a specific mission. The British Air Ministry had reached out to American oil companies in 1938, seeking help developing a fuel specifically designed for the Rolls-Royce Merlin engine that powered the Spitfire and Hurricane fighters. Sweeney's team included Charles E. Starr, both American citizens, and Alexander R. Ogston and P.H. Holt, who were British citizens. Working primarily at Esso Laboratories in Baton Rouge, Louisiana, and Abingdon, England, they created what became known as BAM 100, British Air Ministry 100-octane fuel. The designation was actually 100/130, because the fuel's performance rating went even higher when used in rich mixture settings during takeoff and combat situations. The development of BAM 100 required solving numerous technical challenges. The fuel had to remain stable during long ocean voyages. It had to perform consistently across a wide range of temperatures and altitudes. It had to be compatible with existing fuel systems and seals. And critically, it had to be producible in the massive quantities that a war would require. The solution involved a careful blend of components. High-octane gasoline from catalytic cracking formed the base. Additional aromatics like toluene and xylene increased the octane rating further. And perhaps most importantly, tetraethyllead was added as an anti-knock agent. This lead compound, added in carefully controlled amounts, dramatically increased the fuel's resistance to detonation. The resulting mixture was far more complex than simple distilled gasoline. In fact, to many traditional petroleum engineers, it seemed almost impure, a Frankenstein blend of components that by all rights shouldn't work as well as it did. But work it did. In June 1939, the first tanker load of BAM 100 left the Esso refinery in Aruba, bound for England. The timing was providential. Just 3 months later, Germany invaded Poland and the Second World War began. The British had begun stockpiling this revolutionary fuel, but few yet understood just how crucial it would prove to be. Through the fall and winter of 1939 and into the spring of 1940, the RAF began the complex process of converting their fighter aircraft to use the new fuel. It wasn't simply a matter of filling tanks with different gasoline. Engines had to be retuned, compression ratios were adjusted, spark timing was optimized, fuel mixture controls were recalibrated. The Merlin engines in particular were modified to take full advantage of the new fuel's properties. The work was still underway when disaster struck in May 1940. Germany launched its blitzkrieg attack through the Low Countries and into France. The British Expeditionary Force, along with French armies, were thrown into chaos. RAF fighter squadrons operating from bases in France suddenly found themselves in desperate combat against the Luftwaffe, and the painful reality became immediately apparent. German fighters held the advantage. Messerschmitt 109s could climb faster than Hurricanes and Spitfires still running on 87-octane fuel. They could reach higher altitudes. They could accelerate away from danger. RAF pilots fought with skill and courage, but they were operating at a disadvantage dictated by the laws of chemistry and physics. The evacuation from Dunkirk saved over 300,000 British and French troops, but it was a defeat nonetheless. France fell, and Britain stood alone. The German High Command began planning Operation Sea Lion, the invasion of the British Isles. But first, they needed to achieve air superiority. Luftwaffe bombers began attacking British shipping in the Channel. Fighter sweeps probed Britain's air defenses, and then, in July 1940, the Battle of Britain began in earnest. But by this time, something had changed. Through the frantic weeks of May and June, RAF ground crews had been working around the clock completing the fuel system modifications. By the time the main German assault began, virtually every frontline RAF fighter had been converted to use BAM 100, and German pilots were about to receive a very nasty surprise. The difference was dramatic and immediate. A Spitfire running on 100-octane fuel was 25 miles per hour faster at sea level than the same aircraft on 87-octane. At 10,000 feet, the speed increase was 34 miles per hour. Rates of climb increased by 500 to 1,000 feet per minute, depending on altitude. The Hurricane saw similar improvements. Suddenly, aircraft that had been struggling to match German performance were now superior in most regimes of flight. Luftwaffe pilots couldn't believe what they were encountering. These were supposedly the same aircraft they had been fighting over France just weeks before, the same Spitfires and Hurricanes. But now they were faster, could climb higher, and could engage in combat at altitudes the Messerschmitts couldn't effectively reach. German intelligence was baffled. Reports came back of British fighters performing impossibly well. Some German pilots claimed the British must have deployed entirely new aircraft designs. The truth only emerged when a Spitfire was forced down relatively intact in occupied Belgium. German technicians swarmed over the wreckage, examining every detail. They tested the fuel remaining in the tanks and were shocked by their findings. The British were using fuel with an octane rating far higher than anything the Germans had. The Messerschmitt 109E, the Luftwaffe's primary fighter, couldn't even use such fuel. Its engine wasn't designed for it. Running 100 octane in a Messerschmitt would cause even worse knock and detonation than the British had suffered with lower octane fuel. The German aviation industry scrambled to respond. They began developing new fuel formulations and engine modifications. But they faced a fundamental problem. Germany lacked the petroleum resources of the United States. They had to rely heavily on synthetic fuel produced from coal through the Fischer-Tropsch process. While this could produce adequate fuel, it was extremely resource-intensive and couldn't easily be adapted to produce the high octane ratings the Americans and British were achieving with advanced refining techniques. Moreover, Germany lacked access to the specific catalysts and refining infrastructure needed for large-scale catalytic cracking. The technology was closely guarded, and American oil companies were certainly not sharing their secrets with the Nazis. Germany could produce 100 octane fuel in limited quantities, but never in the volumes needed to fuel their entire air force. The impact on the Battle of Britain was decisive. While German skill and determination were formidable, and while the battle remained desperately close, the fuel advantage allowed RAF pilots to consistently engage German formations on favorable terms. Combined with radar early warning, fighting over home territory where downed pilots could be rescued, and the extraordinary courage of the few, as Churchill called them, Britain held. The Luftwaffe's daylight bombing offensive was defeated. Operation Sea Lion was postponed indefinitely. Hitler turned his attention east toward the Soviet Union, buying Britain precious time to rearm and regroup. But the fuel revolution was just beginning. As America was drawn into the war after Pearl Harbor in December 1941, the importance of high-octane aviation fuel became even more apparent. And nowhere was this more critical than in the massive strategic bombing campaign that would eventually bring the war to Germany's industrial heartland. American heavy bombers, the Boeing B-17 Flying Fortress and the consolidated B-24 Liberator, were designed from the outset as high-altitude strategic bombers. They were meant to fly deep into enemy territory, strike specific industrial targets with precision, and fight their way back home. But this mission profile placed enormous demands on their engines and fuel systems. Both bombers were powered by variants of air-cooled radial engines. The B-17 used 4 Wright Cyclone engines, each producing around 1,200 horsepower. The B-24 used Pratt and Whitney twin Wasp engines with similar power output. These engines were marvels of engineering, but they faced a significant challenge. To achieve the high altitudes needed to avoid the worst of German anti-aircraft fire, they required turbo superchargers that compressed incoming air to maintain power in the thin atmosphere above 20,000 feet. But supercharging created intense heat and pressure in the combustion chambers, exactly the conditions that caused knock. Running these engines at the power levels needed for combat operations with anything less than the best fuel available would have been disastrous. Engine failures would have been constant. Bomber losses would have been catastrophic even before considering enemy action. The United States Army Air Forces specified 100 octane as the minimum fuel grade for all combat aircraft. But American fuel technology didn't stop there. Throughout 1942 and 43, chemists continued pushing the boundaries. They developed 100/130 octane fuel as a standard grade, matching what the British were using. Then they went further. In January 1944, a new fuel designated 100/150 was introduced. This fuel allowed engines to be operated at manifold pressures, that would have destroyed them with earlier fuel. Testing showed dramatic results. The P-38 Lightning, which had been limited to 60 inches of manifold pressure, could now safely run at 70 inches. Its speed increased by 20 to 25 miles per hour. Rate of climb improved by 500 feet per minute. For heavy bombers, the benefits were even more significant. Higher octane fuel didn't just mean more power, although that was certainly valuable. It also meant better fuel efficiency at cruise settings. Engines running on 100/150 could produce the same power as engines on lower octane fuel, but while consuming less fuel per hour. This might seem like a small difference, but over the course of a mission lasting 7 or 8 hours or more, it added up. A B-17G Flying Fortress had a normal operational fuel capacity of 2,810 gallons. With this fuel load carrying a 6,000-pound bomb load, it could fly approximately 2,000 miles. This was sufficient for many missions from bases in England to targets in Germany and back, but it limited how deep into German territory the bombers could strike. And it left little margin for error, for headwinds, for combat maneuvering, for diversion to alternate landing fields if the weather closed in on the home base. The improved fuel efficiency from high-octane fuel effectively extended the bomber's range. Depending on various factors, including altitude, airspeed, and power settings, estimates suggested that 100/150 fuel could extend range by anywhere from 15 to 25% compared to lower octane alternatives. For a bomber with a base range of 2,000 miles, this translated to somewhere between 300 and 500 additional miles of range. That extra range meant the difference between targets that were unreachable and targets that were now vulnerable to American strategic bombing. This became crucial in the great aerial campaigns of 1944 and 45. The Combined Bomber Offensive, as it was called, aimed to systematically destroy Germany's ability to wage war. American bombers struck by day, British bombers by night, in round-the-clock attacks that gave German defenses no respite. Targets included aircraft factories, ball-bearing plants, oil refineries, railway yards, and eventually, as the war progressed and strategic bombing evolved into area bombing, German cities themselves. Every additional mile of range opened up new targets. It allowed bombers to strike facilities that Germans had thought were safely out of reach. It provided operational flexibility, allowing mission planners to route bomber streams around the heaviest concentrations of German fighters and flak. It meant that bombers that suffered damage or encountered unexpected headwinds still had a chance of making it home. The 8th Air Force, operating from bases in England, grew into the largest air force in history up to that time. At its peak, it could dispatch over 2,000 heavy bombers on a single mission. Keeping these aircraft supplied with fuel was a logistical challenge of staggering proportions. Each bomber could consume several thousand gallons in a single mission. With multiple missions per week, the fuel requirements were measured in millions of gallons per month. Tankers carrying aviation fuel crossed the Atlantic in convoy after convoy, braving German U-boats and winter storms. The fuel was piped inland from ports to storage depots, then trucked to the dozens of airfields scattered across East Anglia. Ground crews worked through the night to fuel aircraft before dawn takeoffs. The entire operation was a testament to American industrial capacity and organizational skill. But it all depended on that revolutionary fuel, that supposedly impure mixture that traditional petroleum engineers had once dismissed, the catalytic cracking units that Houdry pioneered, the refining techniques that Palooka and others had developed, the careful blending formulations that Sweeney's team had perfected. Every gallon of 100-octane fuel represented the culmination of decades of chemical research and industrial development. The Germans, despite their own considerable scientific expertise, could never match this fuel production. They developed their own high-octane fuels, designated C2 and C3, that were roughly comparable in quality. Late in the war, German C3 fuel actually had octane ratings approaching 150, but they could only produce it in limited quantities. The majority of German aircraft flew on lower-grade fuels, and this put them at a continual disadvantage. German pilots developed tactics to compensate. They would position themselves above American bomber formations, then dive down through the escorts in slashing attacks, using gravity to augment their engine power. They would break off and dive away before American fighters could catch them. But these tactics, while sometimes effective, were fundamentally defensive. They disrupted bombing accuracy and shot down some aircraft, but they couldn't prevent the bombers from reaching their targets mission after mission, week after week, month after month. The fuel advantage extended to escort fighters as well. The P-51 Mustang, perhaps the finest fighter of the war, owed much of its success to high-octane fuel. Its Packard-built Merlin engine, derived from the same Rolls-Royce design that powered Spitfires, was optimized for 100-150 fuel. This gave it the power to escort bombers all the way to Berlin and back, a range that had seemed impossible just a few years earlier. The P-47 Thunderbolt, another superb escort fighter, used a massive Pratt and Whitney R-2800 engine that generated over 2,000 horsepower with the best fuel. It could absorb tremendous battle damage and still bring its pilot home. And the P-38 Lightning, despite various technical challenges, was uniquely valuable for its twin-engine redundancy and long-range capability, all made possible by high-octane fuel. As the war progressed, the strategic bombing campaign grew increasingly effective, not just because of improved tactics and training, not just because of better aircraft and equipment, but because high-octane fuel made it all possible. The fuel gave American bombers the range to strike any target in German-held territory. It gave escort fighters the capability to accompany them. It meant that even when weather or combat damage forced diversions, aircraft had the fuel reserves to reach safe landing fields. The impact went beyond Europe. In the Pacific theater, the vast distances involved made fuel efficiency even more critical. American bombers island hopping across the Pacific needed every bit of range they could get. The B-29 Superfortress, which ultimately delivered atomic weapons against Japan, depended on advanced high-octane fuel to achieve its design performance. It couldn't have reached its targets otherwise. There's a poignant detail about high-octane fuel that speaks to just how crucial it was. When American forces overran German airfields late in the war, they sometimes found intact German aircraft that had been abandoned. American pilots occasionally attempted to fly these captured planes using standard American fuel. The results were universally disappointing. Messerschmitts that had been fearsome opponents in German hands were sluggish and underpowered when fueled with 100 octane designed for different engines. German aircraft simply weren't designed to take advantage of such fuel. Their engineers had been forced to optimize for what they had available, not for what the Allies could produce. Similarly, when American aircraft had to operate on lower-grade fuel due to supply disruptions or in forward areas where only basic fuel was available, their performance suffered dramatically. Pilots reported reduced speed, lower ceilings, increased fuel consumption. The difference was immediately noticeable and operationally significant. High-octane fuel wasn't just an advantage. In many cases, it was absolutely essential for the mission. The scientists and engineers who developed this fuel received little public recognition during the war. Their work was classified, both to protect industrial secrets and to prevent the enemy from understanding the full extent of Allied fuel capabilities. Men like Houdry, like Palooka, like Sweeney worked in relative obscurity, while the pilots and crews who depended on their innovations flew into history. But those who understood aviation, those who grasped the complexities of engine performance and operational range, They knew the truth. Air Chief Marshal Arthur Tedder of the Royal Air Force, speaking after the Battle of Britain, identified three factors that contributed to British aerial victory: the skill and bravery of the pilots, the Rolls-Royce Merlin engine, and the availability of suitable fuel. He listed them in that order, but one could argue that without the third, the first two would not have been enough. American bomber crews preparing for missions over Germany might not have known the name Eugene Houdry or understood catalytic cracking, but they knew that when they pushed throttles forward for takeoff, when they climbed to altitude over the North Sea, when they held formation through flak and fighters, their engines would respond with power and reliability. They trusted the fuel that filled their tanks, that supposedly impure mixture that had seemed like sludge before chemists learned to transform it. The strategic bombing campaign against Germany has been extensively studied and debated by historians. Questions about its effectiveness, its morality, its impact on the war's outcome continue to be discussed. But one fact is indisputable. The campaign depended absolutely on aviation fuel of a quality and in quantities that no other nation could match. Without that fuel, American bombers could not have reached their targets. Without that fuel, the 8th Air Force could not have sustained operations. Without that fuel, the entire strategy would have collapsed. This isn't to diminish the importance of aircraft design, of tactics and training, of the extraordinary courage of air crews who flew mission after mission, knowing they faced a statistical certainty of being shot down eventually. All of these factors mattered enormously, but they all depended on a foundation of advanced fuel technology that gave Allied aircraft capabilities German engineers couldn't match. The legacy of this fuel revolution extended far beyond World War II. The catalytic cracking technology pioneered by Houdry and others became standard in the petroleum industry. Today, virtually all gasoline goes through some form of catalytic processing. The chemistry that turned waste into high-octane fuel helped establish American dominance in petroleum refining that lasted for decades. The lessons learned about engine performance and fuel formulation influenced everything from automotive engineering to rocket propulsion. Some of the scientists involved went on to contribute to the space program. The principles of managing combustion chemistry in extreme conditions applied equally well to rocket engines as to piston engines. Frank Walker, a young Pratt and Whitney chemical engineer who would later make crucial contributions to water methanol injection systems during the war, eventually worked on propulsion systems for spacecraft. His path from aviation fuel to space-age rocketry illustrated how wartime innovations could be transformed for peaceful purposes. But perhaps the most important legacy was simpler and more direct. High-octane fuel, that impure mixture that shouldn't have worked as well as it did, gave Allied bombers the range to win the war. It extended their reach by those crucial extra hundreds of miles. It meant targets that seemed safe were actually vulnerable. It meant bomber crews that might have run out of fuel over enemy territory made it home. It meant missions that would have failed instead succeeded. When you add up all those missions, all those targets, all those aircraft that made it home when they otherwise wouldn't have, the cumulative impact becomes clear. The fuel didn't win the war by itself, no single factor ever does. But it was absolutely essential to how the Allies fought and won the aerial campaign over Europe. Years after the war, when historians interviewed veterans and analyzed documents, when they pieced together the story of how the Allies achieved victory, the importance of fuel emerged again and again. In memoirs and official histories, in technical analyses and personal accounts, the same theme repeated. The Allies had better fuel. And that difference mattered. There's a particular irony to the story. Germany had some of the world's leading chemists. The German chemical industry was advanced and sophisticated. They understood the science of fuel as well as anyone, but they lacked the resources, the petroleum, the industrial infrastructure to implement what they knew. They were forced to make do with what they had, to be clever with limited means. The United States, conversely, had vast petroleum reserves and an industrial capacity that dwarfed all other nations combined. When American chemists developed revolutionary new processes for refining fuel, American industry could scale up production almost immediately. Refineries could be built, expanded, modernized. Tankers could be constructed to transport fuel across oceans. The entire logistical system could be mobilized to ensure that every Allied aircraft had access to the best fuel available. This illustrated something fundamental about the Second World War. It was as much a contest of industrial capacity as of military skill. The side that could produce more, that could innovate faster, that could translate scientific knowledge into operational capability most effectively, that side held an advantage that would ultimately prove decisive. And in the realm of aviation fuel, the advantage belonged entirely to the Allies. As the war drew to a close in 1945, as Germany surrendered and Japan capitulated after atomic weapons demonstrated yet another form of American technological superiority, the Allied air forces had proven beyond any doubt the importance of strategic bombing. Whether one agreed with the strategy or questioned its morality, its effectiveness in destroying enemy industrial capacity was clear, and none of it would have been possible without fuel. Not just adequate fuel, not just sufficient fuel, but fuel that was genuinely superior to what the enemy could produce. Fuel that gave every bomber, every fighter, every operational aircraft that crucial margin of performance that could mean the difference between success and failure, between life and death. The chemists who created this fuel, men like Houdry, who saw potential in waste, like Palooka, who industrialized the process, like Sweeney, who perfected formulations for specific applications. They were as much warriors as any pilot or soldier. Their weapon was knowledge. Their battlefield was the laboratory and the refinery, and their victory was measured in octane numbers and extra miles of range. So when we remember the Second World War, when we honor the sacrifices and celebrate the victories, we should remember that among all the factors that contributed to Allied success, one of the most crucial came from a laboratory, not a factory floor. It came from minds that understood the invisible world of molecules and chemical reactions. It came from the patient work of scientists who transformed what others considered worthless into something precious. It came from one chemist's realization that impure wasn't the same as useless, that what looked like sludge could become something remarkable if treated correctly, that the heavy fractions everyone else discarded contained within them the potential for fuel so pure, so powerful, that it would help win a war. And when bomber crews climbed into their aircraft on cold English mornings, when they ran through pre-flight checks and heard their engines roar to life, when they set course for Germany knowing the mission would push them to the limits of their aircraft's capabilities, they depended on this fuel. They depended on those extra 500 miles of range that made the impossible possible. They depended on chemistry they didn't understand, created by men whose names they didn't know, through processes that would have seemed like magic to earlier generations. But it worked. It gave them the power and the range and the reliability they needed. And in the end, that was all that mattered. The war ended. The veterans came home. The aircraft were retired or scrapped. The bases were closed. But the fuel technology remained, becoming the foundation for everything that followed in aviation. Every time a modern aircraft takes off, it uses fuel refined through processes that trace their lineage back to those wartime innovations. Every time a pilot pushes throttles forward and feels engines respond with smooth, knock-free power, they benefit from discoveries made under the pressure of war, when failure would have meant not just a crashed aircraft, but potentially a lost cause. This is the story of how chemistry changed history, of how one impure mixture gave Allied bombers 500 miles more range, of how that range translated into targets destroyed, missions completed, wars won. It's a story that deserves to be remembered, not just as a footnote, but as a central chapter in understanding how the Second World War was fought and won in the skies over Europe. The men who flew the missions earned their place in history through courage and sacrifice. But the men who made those missions possible, who gave those aircraft the fuel they needed to reach their targets and return home, they too deserve recognition. Their battlefield was different, their weapons were knowledge and chemistry, but their contribution was no less vital. In the end, the lesson is clear. Wars are won not just by those who fight, but by those who enable the fighting. And sometimes, the most crucial enabler is something as simple and as complex as the right fuel in the right place at the right time. That impure mixture that gave bombers an extra 500 miles of range. That revolutionary technology that turned waste into warfare's most crucial commodity. That triumph of chemistry over constraint, of innovation over limitation, of human ingenuity applied to the most desperate of circumstances. This was the fuel that helped win the war. And the story of how it came to be, how it was created by chemists who refused to accept that waste had to remain waste, how it gave Allied bombers capabilities the enemy couldn't match, that story deserves to be told and remembered. Because it reminds us that victory comes in many forms, and sometimes the most important battles are fought not with guns, but with test tubes, not on battlefields, but in laboratories, not by soldiers, but by scientists who understood that even something as seemingly mundane as fuel could change the course of history.